Okay, let's get started. Welcome to Lecture 8 of the planets. Today we're going to move into a totally new topic, and it's a topic near and dear to the hearts of all astronomers, but also to physicists, chemists, biologists, medical practitioners, whether you're a physician, a nurse, or a researcher in medicine. And that topic is light. The nature of light, how light is produced, absorbed, and how light can be used as a stethoscope, if you will, to diagnose the composition, temperatures, and the interior nature of many, many types of objects across the universe and within a hospital. So we'll be talking about what light is composed of and how you can play with light. Let me give you a little bit of logistical news. Some of it is important. I'll remind you that this week now we're moving to Chapter 5 in order. You should definitely read Chapter 5. I always emphasize how valuable the reading of the chapter is, and in this case, you really will benefit a lot. The nature of light might be somewhat new to you. You'll see in today's lecture and Thursday's lecture that the nature of light has some complexities. So you'll want to sit in a comfortable chair for 3 hours and read about the nature of light and how you can make use of it. There's, of course, homework on Chapter 5, as always, due Friday at 6 p.m., this coming Friday, as usual. And you'll see the assignment number 5 for Chapter 5 there. And then, in addition, there is some rather grim news on the horizon, and that is the nasty business of a midterm. It is finally coming. And the midterm is a week from today. Let me tell you a little bit about it. It's in class right here. I hope you'll spread yourselves out to give yourself room, especially sitting far from your neighbors, your friends. Better to not let your eyes even be tempted. So by all means, give yourself a lot of space. You can sit up front if you want for the midterm. It will be covering chapters 1 through 5. In other words, including today's lecture, Thursday's lecture, and the homework from Chapter 5. There will be about 30 multiple choice questions, all multiple choice. We will provide the Scantron forms for you, so there's no reason to buy anything. You don't need a calculator. We'll make sure that all of the problems can be done without a calculator. And then just to give you some clues as to how to study, here are some ideas. First of all, the problems will all be based on what's in the chapters, the book, in other words, the first 5 chapters. Obviously, the questions will emphasize the issues that were discussed in lecture. So by all means, go back and re-look at the PDFs of my lecture presentations that are online. And I think almost all of the audio is also online now if you want to hear the lecture as well as see the presentation. And then, of course, the homework will also, the midterm will be based quite a bit on the homework. So I can promise you that in making up the midterm, we are glancing at the homework problems and trying to make up midterm questions that are cousins of the homework questions. So by all means, studying the homework, studying the lectures, and rereading the chapters of the book are the best way to study. Let me ask, are there any questions about the midterm at this point? Anyone have a question? Yeah.
How much time will we have?
You'll have an hour and 15 minutes. So from 10 after until 25 after 6. Yeah.
Will you release any practice midterms?
I don't have any practice midterms, unfortunately. This midterm that we will be giving, the GSIs and I, is different from any other midterm. And you may well find midterms in this course, and that wouldn't hurt if you can find them somewhere, but I can promise you this midterm will be somewhat different from those in a sort of structural way. Did you have a question? Yeah.
If there's any topics in the book that haven't been really discussed in lecture, are you going to still put that?
It's possible. I'll repeat the question. Is it possible that the midterm could harbor some questions that were not in lecture but were in the book? And the answer is yes, there could be some questions that are in the book. Or I'll put it a little more precisely. There could be topics that I just lightly covered in lecture, but the book goes into greater depth, and so the book is a better resource. Any other questions? Yeah. Will the midterm be weighted? You mean will it have mass or weight? Is that what you meant? Weighted in what way? You mean relative to the other midterms? The midterm, every problem is going to be independent of every other problem, and you either get it right or you don't get it right, and you'll get a total score when it's all done. So there's no real weighting of the problems. I think all of the multiple choice questions will be worth the same amount, if that's partly what you're asking. Anything else? Yeah. Yeah, what's with that camera guy? I don't know. Who knows? Yeah. So let me remind you of the grading in this course. The question is something about a curve. I heard curve. I'll remind you that the grading, as I mentioned, the first couple of lectures is on an absolute scale. 90 to 100 is an A, 80 to 90 is a B, and so on. So it's pretty straightforward. Anything else? Okay. Let me then touch on one other topic. Oh, let me say one thing. During the upcoming week, very good idea to attend discussion section, because more than ever, the GSIs will offer you a chance to review topics. You can ask them any question about anything in all 5 chapters during the discussion sections. Office hours, the same thing. It's open field. Feel free to come to my office hours or the GSI office hours and ask anything that you've run into. Email also works, so feel free to send us emails and we'll try to answer your questions as you're studying. Okay? All right, one last logistical issue. I want to remind you about the Observing Project. This is a reminder, and I'm showing you the picture of the twilight sky again I showed before, where Antares, Saturn, and Mars were on September 5th. Of course, we are well past September 5th. I can assure you that Antares and Saturn in its long period orbit have not moved very much, but Mars, closer to the sun, may have moved. And your job, to remind you, is to make a sketch of these 3 objects in the twilight sky. It has been difficult the last week. I've been watching every night, and many of the nights there were clouds. So if you tried to look, you were disappointed. Last night was spectacular. I hope some of you took advantage of the clear night last night. I think tonight will be cloudy. I hear a storm is coming in Wednesday and Thursday, so you might start thinking toward making sure that you're out with a clear view of the southwest on Friday or Saturday or Sunday night. And I've extended this all the way to, where did I say it? October 1st. So feel free to take data, if you will, on Antares, Mars, and Saturn through October 1st, with the due date being October 2nd. And I promise you it's well worth it. Last night I went out, I found a hill, I walked up a hill, and I got a nice view. This is a picture I took with my iPhone. I was lucky enough to get to see some Berkeley city lights, and those are not the exact positions of the 3 objects, but the question really is, given Antares and Saturn, where in fact is Mars now. It's pretty exciting. If you got a chance to already take some data, you may get an opportunity to actually see Mars orbiting the sun. Okay. Yes. Do you have to write? Oh, just one paragraph total. Yeah. 3 or 4 sentences explaining what you saw and why whatever moved, why it might have moved. Okay? Any other questions? Yeah.
2 questions. One, where did you take that picture? And the other is, if I got one observation in like Danville, which is like 30 miles away,
No problem.
and then one here, that's fine.
Danville's fine. The universe doesn't care where you are. And where did I take this picture? I simply walked up, I walk every day if I want a clear view. I walk up Bancroft or I walk up Hearst. I go up near the dorms, near the Memorial Stadium. Anywhere I'm up a little bit above the buildings, a 3-minute walk so that the buildings are sort of eye level or a little bit above eye level. You can see these are pretty low in the sky. So it's tricky to see them. If you have buildings or trees in the way, you'll miss them. And the timing is critical. After sunset, maybe 25 minutes or so, it gets darker and darker and darker, and finally you can see them. Okay. Turn over a new page, at least mentally, in your notes. I hope you're not taking notes. Today we're going to discuss the most important way that scientists can actually sense the nature of the rest of the universe. Think about it for a second. We humans don't have access to the planets, the stars, and the galaxies. We can't go out and do experiments at a neighboring star or galaxy. They're simply too far away, making them inaccessible. And so the way that astronomers can learn about the nature of these distant objects is by receiving the light that they emit, or maybe the light that reflects off of them, and analyzing that light to learn something about the atoms, the molecules, the temperature, maybe the magnetic field, or the velocity even of those objects. And you'll see there's an enormous amount of information we can learn about planets, stars, galaxies, and even the gas in between the stars by simply analyzing the light that comes from all of those objects. It's an incredibly powerful technique, using light as our tool to probe the nature of the cosmos. So let's start by describing light. All of you know something about it from high school. Light carries energy, and we measure the amount of energy carried per second in a unit called watts. All of you know about watts. I'll describe it in a moment. Light also has a wavelength, we'll talk about that, and a frequency of vibration. So I'll be describing the nature of wavelengths and frequencies of light. Also, light exhibits something called the Doppler effect. You've all heard about it. I'm going to tell you in detail how the Doppler effect works. Now, just to give you the backdrop, a dwarf planet like this one, Eris, it's nothing more than a tiny dot of white light in a telescope. Even the Hubble telescope only sees a tiny dot of light. How do we know what a distant dwarf planet orbiting the sun beyond Pluto might be made of? Well, we actually have to analyze it using the light. This is an artist's rendering. How would we know the color, the rocky composition, the chemicals of which that dwarf planet is made? Well, we analyze the light to learn the chemical composition of the surface and of the atmosphere. Whoop, there goes more equipment. You happy? Yes. Uh-oh, watch out for this. We can actually learn the temperature of a distant planet from the light. We can determine whether that distant object is made of rock or ice, liquid water, some other form of liquid, and indeed also if it's made of gas, all by analyzing the light coming from those objects. So let me remind you of some of the things you already know about light and maybe tune up your knowledge. Light is a form of energy. It carries energy. It's composed of different colors. You all know the colors of the rainbow. Each of those colors is a different wavelength of light, or in other words, a different frequency of light, and I'll be describing that in a moment. Where does light come from? In this room, why is there light hitting me? Where does that light come from? And how can light be absorbed? We'll learn in today's lecture that it is atoms and molecules that can emit light, and you'll learn how. And atoms and molecules can also absorb light. And I'll be describing the quantum mechanics of the emission of light and the absorption of light. It's really quite exciting. So a little about the energy. You're going to be hearing about the energy associated with light, especially sunlight, for the rest of your lives. And I'll remind you that the concept of power is the rate at which energy is emitted or used up, and power has units of watts. You all know this. You go to the store, you buy a light bulb. It's a 100-watt light bulb or a 50-watt light bulb. What does that mean, 50 watts? It's how much energy the light bulb uses per second. So a watt is an energy rate over time. The unit of energy in the metric system is the joule, and so a watt, being energy used per second, has units of joules per second. So a joule per second is a watt. A 100-watt light bulb is using up 100 joules of energy per second. And that's something that I think you're all familiar with, as you can see in the picture, by purchasing light bulbs. Here's a quiz that you don't need your colored pieces of paper for, just a quick quiz. What is a kilowatt hour? And by the way, why am I asking? Well, I'm asking because some of you have received an energy bill, or you've seen your energy bill, your electric bill. And when you get this in the mail, you have to pay some number of dollars per kilowatt hour. What is a kilowatt hour? Well, if you break down the word carefully, there's watt, that's energy per second. Kilo means 1,000 of them, so a kilowatt is 1,000 joules per second being used up. And then the hour means that the rate, a kilowatt, over the course of the duration being 1 full hour. So if you have a kilowatt light bulb on for 1 hour, there's a certain total amount of energy that's been used. Notice something wacky here. This is almost embarrassing. A kilowatt is energy per second, but an hour is time. So energy being used per second times a time gets you back the energy units that you had in the first place. So a kilowatt hour is some number of joules. Why it is that the power companies don't give us a bill for the number of joules we've used, I don't know, but they bill us in terms of how many kilowatt hours you used at the end of the month. So how many joules is a kilowatt hour? How many joules are there in a kilowatt hour? Well, break it down. Remember, there's 3,600 seconds in an hour, and a kilowatt is 1,000 joules per second, but now you have to multiply by 3,600 seconds because that's an hour. So 1,000 joules per second times 3,600 seconds means that a kilowatt hour must be, therefore, 1,000 joules times 3,600 seconds, or in other words, 3 million 600,000 joules. That's a kilowatt hour, for what it's worth. And my purpose for showing you this is that for the rest of your life, you will pay with your own money for kilowatt hours. Whenever you use electricity, somebody has to pay for it, and you'll be paying some amount of money per kilowatt hour. And you should remember that you're really paying for the energy you use, not the rate at which you're using energy, the watts, but the total amount of energy itself. Okay. Now, light has properties. I've mentioned a few of them. Let's dig into some of the details. Light can act as a wave, and we'll talk about that. And light can also act as a particle, a so-called photon. So we'll talk about the wave nature of light and the particle nature of light. In either case, light has a wavelength, and I'll define that in a moment, and light has a frequency. And both of those correspond to color, blue, green, yellow, and red. All light, no matter what its wavelength, what its color, what its frequency, all light travels at the speed of 300,000 kilometers a second. I mentioned this in the first and second lectures. And sometimes people just shorten that by saying light travels at the speed of light. Because it's such a famous quantity, it's a constant of nature. We don't know why. Why is the speed of light 300,000 kilometers a second? Nobody knows, but it's a fundamental constant. And in fact, it was Einstein who realized that this fundamental constant determines something about causality when one event causes another event to happen. The speed of light determines something about the frame of reference you can be in and still have one thing cause another thing. So the speed of light is intimately connected with philosophy, the causality of the universe, that nothing can just happen by itself, something else has to cause it to happen. Now, let me remind you about waves. You're all familiar with this. Waves have a certain nature. They carry energy. Let me see if I can find my cursor. As always, I have to look for it. You're familiar with water waves, maybe not so much light waves. And just to remind you, water waves are easily launched by throwing a rock in a lake. Notice the waves launched by that perturbation of the water. The waves clearly have properties. There's a distance between the wave crests. That distance, as you'll see in a moment, is the wavelength. The leaf bobs up and down with a certain frequency, some number of times per minute. We'll talk about that in a moment. And furthermore, the water wave here, an analogy with light waves, the water waves clearly carry energy. How do you know? Because when the wave hits the leaf gains kinetic energy. It moves. Let's show it again. Watch the leaf actually gain kinetic energy from the water wave. That oscillatory motion gives it kinetic energy 1/2 times its mass, m, v squared, the velocity squared. So it's pretty exciting to think about water as water waves as carrying energy, and so do light waves. They carry energy. Now let me talk about the properties of a wave. I've mentioned now several times that all waves, and in particular light waves, have a wavelength and a frequency. And let me show you what I mean by that. What you see here is, again, a water wave to get us warmed up. There's the water wave. The leaf is bobbing up and down. The wave carries energy. It also has a wavelength and a frequency. Let me describe them. Up here you see a diagram of the water wave, which is a good analog of the light wave. and there's a distance between the wave crests. That distance between wave crests is called wavelength. So the wavelength of any wave is the distance between the crests, or if you prefer, the distance from one trough to the next trough, minimum to minimum. That's the wavelength. What about frequency? Well, if you watch this leaf, or the wave itself, every time it reaches a maximum, the light blinks, just to give you a reference. And the number of blinks per minute is the frequency of the wave. How many wave crests pass by per minute? So frequency has units of 1 divided by time, minutes, seconds, hours, whatever. So this leaf has a certain, the leaf is showing you the frequency of the wave going by, if you couldn't see it already. And just for comparison, up above here is shown a caricaturization of a light wave. A light wave is due to electric and magnetic phenomena, electric fields and magnetic fields, and we're not going to go into them, but there is actually an electric force, if you will, and a magnetic force propagating along with a sine wave, if you remember sine waves from trigonometry, very much like the sine waves of the water wave. So light waves are a sine wave, water waves are sine waves. In the case of water, it's the water that's the medium, and in the case of light waves, there actually is no medium. Light can travel in a vacuum, but the light consists of electric fields and magnetic fields oscillating up and down as they move along. Okay. So to summarize, light waves have a frequency. We use the letter F to denote how many oscillations occur per second or per minute. The distance between the wave crests is the wavelength. We use the Greek letter lambda to denote that distance, the wavelength. And amazingly, there is a close, intimate relationship between the frequency of a light wave and the wavelength of the light wave. And that relationship is that the frequency of the wave times the wavelength of the wave is equal to the speed of the wave. In fact, this equation holds true for all types of waves, not just light waves, but also water waves, sound waves, seismic waves that travel through the earth, and so on. The speed is always equal to the frequency times the wavelength. So if the speed of light is a constant, which I said it is, then the frequency and the wavelength are inversely related to each other. If a certain light wave has a certain frequency, you can then calculate what the wavelength must be. Knowing the speed of light and knowing that frequency, you can solve for the wavelength. If the light wave has a higher frequency, then it better have a smaller wavelength so that the higher value of f compensates for the lower value of lambda. And so one goes up, one goes down, so that the product, when you multiply them, is still the speed of light. So that's the nature of light waves in general. And this just says what I just said. If f goes up, lambda goes down, and vice versa. Now, I haven't explicitly said this, but let me now say it. The wavelength of a light wave is what we humans sense as color. When you see something blue, that blue light has a certain frequency that our brain interprets as blue. Red light has longer wavelengths, blue light, short wavelengths, yellow and green have wavelengths in between. And I'll show you what I mean with this demo. So here's shown a schematic of a light wave again. Notice that there is a wavelength the distance between the wave crests. And there's a frequency, how often the wave crest goes by per minute, say. And with this little demo, I can give you a sense as to what happens if you change the wavelength of light. Go from a certain color to some other color. The speed of light stays the same, but the wavelength and the frequency change in a reciprocal, inverse way. So, for example, with this slider here, I can change the wavelength or frequency of light. Right now it's set at red, you see, right there. Let me change that color to blue. Watch what happens. Blue light has a shorter wavelength and a higher frequency. Wavelength went down, frequency went up when you compare blue light to the original red light. Red light, remember, has a longer wavelength and a lower frequency. Yellow light in between, green light also in between, and blue and toward the violet is where the wavelengths are the shortest and the frequencies are the highest. The speed of light stays the same the whole time. The speed at which that wave train goes from left to right stays the same. Okay? So wavelength and frequency trade off from each other. Okay. Now, I think all of you had a pretty good idea of everything I've said so far, but I wanted to say it to sort of bring it back into your consciousness. You know this because whenever you see a prism in your daily life, when sunlight goes through a prism, you know that the white light from the sun spreads out into the different colors of which that white light was composed. What looks like white light actually has all the colors of the rainbow in it. And you know that because when you send white light in, it spreads out through the glass by what's called refraction. And each wavelength of light, i.e. each color, gets bent a different amount. So the red light gets bent differently from the yellow light, from the green light, from the blue light. And because the different wavelengths get bent through the glass by refraction by different amounts, you get to see with your own eye the actual colors that were always there inside the white light, but now they're being spread out. So again, the red light represents long wavelengths. Blue light represents short wavelengths. By the way, just to remind you, when you look at an object and you see it has color, like this chair has a certain blue color, I think all of you can see. Why does this chair look blue? Well, there's two things to be said. If the chair looks blue, that means that most of the light coming from the chair going into your eyes, sensed by your retina, and then interpreted by your brain, most of that light has short wavelengths. Your brain says, hey, here comes some short wavelengths. I see short wavelengths, that looks blue. Your brain does that. The other thing to be said is that this chair does not emit its own light. You only see this chair because of white light coming from the lamps in the ceiling, white light that bounces off of the chair. And you might ask, well, where's all the red light gone, and the orange, and the yellow, and the green? Where did it go? Why do I only see blue? The substance of which this chair is composed, this fabric here, plastic, for whatever reason, absorbs the red light, the yellow, the green, absorbs it, and only reflects the blue light. So this chair looks blue even though white light is hitting it, because it has the ability, the substance of which the chair is made, has the ability to absorb all the other wavelengths or frequencies of light. Rather amazing. And anything that has color that you see in reflection, like your shirt or the something in a store or something on the street, or the leaf of a tree that looks green. Why does a leaf look green even though the sunlight's hitting that leaf? Well, the leaf looks green because it absorbed the blue light and the red light, leaving just the green light to be reflected. So things have color when they're viewed in reflection because of what they absorb and then what's left over to bounce off of it. Now, that brings us to the Doppler effect. You all have heard about the Doppler effect. If you watch television and watch the weather forecast, they talk about Doppler radar predicts rain is coming into the region. Another place you hear about the Doppler effect is when you hear about a police officer can actually monitor the speed of your car using a Doppler radar gun. And so the Doppler effect is used in a lot of different applications. And let me tell you how it works. It's actually very simple. When a car is driving along the street, it's emitting sound waves, not light waves. Well, yeah, there are light waves, but sound waves are what matter because you hear, for example, the siren of the ambulance as it goes by. And so those are sound waves propagating through the air. And if you're standing over here, what happens is that the sound waves are being emitted by the car, but every time the car emits a wave crest, the car moves forward. Oh, I'll go the same direction as the car. The car moves forward so that by the time it emits the next wave crest, the car has caught up a little bit to the previous wave crest. It emits one wave crest, the car moves, then it emits another wave crest, and they get bunched together. So the wavelengths get compressed, get shortened, when the emitter, in this case the ambulance, is catching up to the previous wave crests that it already emitted. That's the Doppler effect, causing the wavelengths to be shorter in the direction it's moving. And of course, conversely, the wavelengths get stretched out in the direction opposite it's moving, because the ambulance moves a little distance before it emits the next wave crest, and by then the previous wave crest has already propagated away by the time the next one's emitted. So there's a bigger gap, a bigger distance between the waves. So waves emitted from an object moving towards you will have its wavelength shortened, and that's the Doppler effect, or lengthened. Here's a little demo. It shows how that works. This is a helicopter emitting sound waves. And let me start the helicopter engine. Here we go. And you can see that, yeah, this isn't light waves, these are sound waves, but the helicopter makes a loud sound. The light waves are going out. Each wave crest comes after the previous wave crest, and there's another wave crest, and so on. And you see the succession of wave crests, sound wave crests, in this case, not light, but sound. And if you're standing there, you hear with your ear and your eardrum the frequency of the light waves. So you can tell the note on the piano, the frequency, the pitch, sometimes it's called, of the sound wave. Now, what if the helicopter is moving toward you? I'll move this little slider. Actually, I'm going to show it again. There's the sound waves with a stationary helicopter. Now let me let the helicopter move toward the person. I'll move this little slider. And here we go. See, the helicopter catches up a little bit to the previous wave crest that was emitted, so the distance between the wave crests gets squashed, gets compressed. And so the wavelength is shorter, the frequency of the arrival of the wave crests will be higher, a higher frequency, and your ear will say, oh, that's a different note on the piano, because the frequency of the note. You all know that on a piano, the note A, right near middle C, has a frequency of 440 hertz, 440A. And so your ear is very good at sensing the frequency of sound waves. And so you can tell the frequency of the sound waves from the helicopter. I'll crank up the speed of the helicopter. Here we go. Go all the way. Ready? And now you see, due to the Doppler effect, the sound waves are even more compressed. In other words, the wavelengths are shorter, the frequency is higher, and your ear would tell that. Of course, the Doppler effect works in the other direction. If I make the helicopter go backwards, by the way, I have no idea how a helicopter would actually go backwards, oriented the way it is. But notice that when the helicopter goes backwards, the succession of wave crests is farther apart, again, because it emits one wave crest, then the helicopter moves back and emits another wave crest, so the distance between them is larger than it would be, and that's the Doppler effect. Okay? All right. By the way, all of you know the Doppler effect. Just to, before I show this, I have a little movie. When you stand near the train tracks and the train is about to go by because you put a penny on the train tracks, but you're hoping nobody will notice. I didn't say that I did this. But if you had put a penny on the train tracks to see what happens when the train goes by, even with your eyes closed, you can hear when the train is coming and when the train is going away, because the train sounds like this. You're hearing the Doppler effect very easily when a train goes by. When a race car goes by at the racetrack, you always hear, "Meow." That's the Doppler effect. And here's a little movie about the Doppler effect. Oh, wait a minute. I didn't give you sound waves from the movie. Oh yeah, what about that penny? I don't know. I don't know what would have happened had somebody put a penny on the... Cool.
Most science.
I think I have a little equation to give you, and then a little more about light. This is the equation that allows you to interpret the Doppler effect. It's a very simple equation, so I wanted to share it with you. When the wavelengths are bunched together so that the wavelengths are shorter, there's a change in the wavelength. There's some wavelength that they had, and now they have a new wavelength, and the change in the wavelength is what we call delta lambda, the change in the wavelength. Here's the original wavelength. So delta lambda divided by lambda is the fractional change in the wavelength. And that's always equal to the speed with which the object is coming at you or going away from you, divided by the speed of light, c. So here's that constant c, the speed of light again. Delta lambda over lambda is equal to the velocity of the object approaching you or receding away from you, divided by c. What does this help you with? Well, if you measure the change in the wavelength of something as the train goes by, as the star approaches you or the planet approaches you or recedes away from you, if you measure the change in the wavelength divided by the original wavelength, you can solve for the speed. So you can learn the speed with which a planet is moving, a star is moving, even another galaxy, as they said in the video, the speed with which another galaxy of stars is moving toward us or away from us. So this is the Doppler formula. Very simple, powerful way to learn the speed of something by simply measuring the amount of the Doppler effect. Okay, now I want to talk about something really important. This is really the guts of today's lecture. How do photons get produced? How does light get manufactured? Where does light come from? Well, to start, I'll remind you that you could have a star or a light bulb emitting light. You gather that light with a telescope. It might have a mirror or a lens in it. And you can analyze the different colors of the photons, blue ones, red ones, yellow ones, depending on their wavelength or their frequency, that are traveling. So the telescope's job is to collect all that light from another star and to analyze which of the photons are red, yellow, green, and blue, and how much of each. Now, each of the photons carries an energy as well as a wavelength and a frequency. And so, in addition to wavelength and frequency, we're going to start talking about the energy carried by a photon. And this is really very exciting and valuable because, as you all know, we humans can make use of sunlight energy. And if we could make use of it efficiently, we could solve some of our energy needs. So making use of the energy of light is very important. So I want to tell you about it. Every photon has a certain energy of its own. And there's an equation for it that's very simple, so I wanted to share that as well. It's the frequency of light, f, that you've already learned about, times a constant of nature, a new constant of nature, called h, sometimes called Planck's constant. Planck's constant. It's another one of these constants of nature that nobody knows why it is we have that constant. No one knows why it has the value that it has, but there's a constant called Planck's constant, and when you multiply it by the frequency of the light, that tells you how much energy in joules there are in a photon. So every photon has a certain amount of energy. And if we could harness that energy, we could make use of it in our daily lives. Now, you can see immediately something quite obvious. Blue light has high frequency. Remember? Blue light, high frequency, and therefore blue light photons that are blue, have more energy than do photons that are red. Remember, the red photons have long wavelength, but low frequency. And so the red light has less energy. And if you're a little puzzled by this, spend a minute and relate again in your mind, connect the frequency of light. Blue light has high frequency, red light has low frequency. Connect those facts with this equation that the energy of a photon is directly proportional to the frequency of the light. So blue photons have more energy than green photons, and green photons have more energy than yellow photons, and yellow photons have more energy than red photons. Okay? Now, of course, all of you know that we can make use of that photon energy, especially the light that comes from the sun, by using photovoltaic panels, photovoltaic cells, solar cells. And so people are now working in Silicon Valley and elsewhere in the world to design better and better photovoltaic cells, solar panels, to convert the light from the sun into electrical energy. Where does that electrical energy come from? The photons. Okay? And here's a little video that talks about that. What I don't get about that video is that the sun is about to set. How is he going to charge his iPhone when the sun is set? He made it sound like, you know, while I sleep at night, I can be charging my iPhone. Well, I promise you the solar cells are not going to work when the sun is down. But obviously during sunup, it will work. Now, I have been mentioning wavelengths of light, and I actually didn't tell the whole truth. I mentioned blue light has short waves, red light has long waves. But what about wavelengths that are shorter than blue light, or wavelengths that are longer than red light? Well, there are light waves that are shorter than blue and longer than red. And in fact, there's a whole suite, a whole set of different wavelengths. The shortest wavelengths of light are called gamma rays, the very shortest wavelengths. The distance between the wave crests is less than 1/billionth of a meter. And then there are X-rays that have slightly longer wavelengths, but still very short. So X-rays are light, just like the light that your eye can see, except that X-rays have such short wavelength, your eyeball cannot see them. Ultraviolet light is another form of light, very short wavelength as well, near the visible. And then there is visible light. There's visible light, about 1/millionth of a meter is the wavelength of visible light, between 4 nanometers, between 400 nanometers and 700 nanometers. Then longer wavelength light than red light is called infrared light. Infrared light is just regular light, but the wavelengths are even longer than the wavelengths of red light. So the photons, if you want to think about it, have lower energy because infrared photons have longer wavelength than red and therefore lower frequency. So HF is lower. So infrared light just has low energy photons. And then the longest wavelength light waves are called radio waves. You've all heard these terms, and that's why I wanted to put them up here. You've heard about X-rays and gamma rays and radio waves. You might not have realized that they were all just light. Different wavelengths, or in other words, frequencies of ordinary light. Our human retina, the human eye, is only sensitive to a tiny sliver of all of the possible wavelengths of light. There's the set of wavelengths your eye can see, blue through red, and that corresponds to a little tiny region of wavelength that I mentioned. Shorter wavelengths extend over many orders of magnitude, factors of 10. Shorter wavelengths, and light also extends many orders of magnitude longer wavelengths. All of them are just part of the so-called electromagnetic spectrum. In other words, light. So whenever you hear these terms, you're just talking about light. By the way, why are we humans so lucky to have eyeballs that are sensitive to visible light? Well, there's a reason, and the reason we'll discuss a little bit on Thursday, but in advance, our eyeballs are sensitive to the particular range of wavelengths, blue through red. That is where the sun emits most of its light. So we humans are the product of evolution, Darwinian evolution. Over the millions and billions of years, eyes have evolved to be most sensitive to the very wavelengths of light that we have around us in abundance, namely light from the sun. Those species that developed eyes that were sensitive to other wavelengths up there were unlucky species. They couldn't see because the sun wasn't emitting light at those other frequencies or wavelengths. And so those species that were fortunate enough to have eyes sensitive to the same wavelengths that the sun emits obviously could see more easily and therefore could survive better, pass on their genes to the next generation, and the next generation would have the same traits of vision that the successful previous species had. So to summarize, light can be thought of as a vibration of an electromagnetic wave. The frequency times the wavelength is the speed of light. Or you can think of light as a particle, in which case there's an energy for each photon, this constant h times the frequency. Now, I want to talk about how light is produced. Where does light come from? The answer is light comes from atoms and molecules. And I promised you I would describe the quantum mechanics of emission of light. And at the same time, I'm going to discuss the quantum mechanics of the absorption of light. So we're going to be talking now about how an atom, in detail, microscopically, how an atom can emit light, create it, and how an atom or molecule can absorb light. And this will be very important, as you'll see. In addition, of course, light can just simply bounce off of an object. When I was describing the chair, I said, well, the chair isn't emitting or absorbing the blue light that you see. It's actually reflecting the blue light. So you might be able to see an object like my shirt by the light that's reflecting off of it. Okay, how do atoms emit and, by the way, absorb light? The clue came many years ago when it was found that certain atoms only emit certain colors. Indeed, each type of atom emits a unique set of colors, or in other words, wavelengths, or in other words, frequencies. Each atom, and indeed each molecule, has a certain set of colors or wavelengths that it emits. Not all of the different colors. And by the way, as we'll talk about in a little while, mostly next time, solid objects like a rock emit all wavelengths of light by something that we call thermal radiation. So we'll talk about how solid objects work that are composed of billions or many more atoms or molecules. But for the moment, we're just going to talk about atoms and molecules. Each atom has its own set of wavelengths that it emits, and the reason is that each atom has a unique set of energy levels that the electrons can live in. Remember, an atom, all of the atoms that you see over here on the periodic table, each atom has a nucleus and some number of electrons buzzing around that nucleus. Those electrons can live in a certain energy level, or a different energy level, or yet a different energy level. And so the electrons can actually change from one energy level they're in to another. And an atom emits, it turns out, its own set of wavelengths. It's like a fingerprint, whether it's potassium, iron, carbon, oxygen. Every type of atom has its own set of energy levels for its electrons, and it emits light of a certain set of wavelengths, like a fingerprint. So I'd like to show you now some examples of the specific colors that individual atoms can emit. And I'm going to show you with this little funny thing here, and then I'm going to show a demo. So what you see here is a little electronic demo. I'm going to click on a button like, say, hydrogen. H, of course, stands for hydrogen. And when I click on it, down below, you're going to see the rainbow of colors, all of the wavelengths of light emitted by that atom, sorted, separated by their wavelength, 400 nanometers, 500 nanometers, 600 nanometers, and so on. From left to right, you will see how much light is emitted by that specific atom. Okay? Let me show you hydrogen to start. If you have good eyes, you can see that hydrogen atoms emit 4 different wavelengths or frequencies of light. A red wavelength, there's a sort of a turquoise, there's a blue, and a violet. Hydrogen atoms only emit those 4 wavelengths. Let me turn off hydrogen and show you what helium looks like. What you're seeing here is what a helium atom emits. Helium atoms emit a red light, yellow, I don't know what that is, a little greenish, green, turquoise, and so on. And that's it. Helium atoms only emit those specific wavelengths. Lithium. Now I'll do carbon. You ready for carbon? Much more rich. Why? As I'll describe in a minute, carbon atoms have many more energy levels for the electrons to be in, and when an electron drops from a higher energy level to a lower energy level, the electron lost energy. If an electron goes from a high energy level to a low energy level in a carbon atom, it has to somehow make up for the loss of energy. Energy must be conserved. And so it does this by spitting out a photon that has exactly the energy difference between the two energy levels. One of my favorites, sodium. There it is. A beautiful set of energy levels allows the electrons to jump from a higher energy level to a lower energy level. And because the electron lost energy, it conserves energy by spitting off a photon that has the energy, HF, equal to the difference in energy between the two levels. And finally, here's neon. A nice, rich set of colors. Okay. I want to show one more slide, and then I'm going to do a demonstration, and some slides are being handed out. By the way, we need these back, so when you get one of these slides with a piece of plastic, please be sure to pass it back in the direction it came at the end of the lecture, because these are expensive and we have only a few of them. So here's the idea, the most important concept of today's lecture. An atom can be thought of as having energy levels, and a given electron can reside, it can live in any one of those energy levels. But it can only live in specific energy levels. We sometimes say discrete energy levels. And when an electron is in a higher energy level and it drops back down to a lower energy level, that electron has lost energy. And if it's lost energy, energy must be conserved somehow. And so the energy that it's lost comes out in the form of light, a photon, of exactly the energy equal to the difference in energy between the two energy levels. So what I'm going to do in this demo is ping the atom. I'm going to kind of jostle the atom, and you're going to get to see, I hope, the electron get excited. It's kind of like taking a little hammer, banging on the atom, bumping the electron to a higher energy level, giving it energy, and then letting that electron drop, and you'll have to watch very carefully. When the electron drops down, it will be losing energy and spitting off a photon equal to the difference in those two energy levels. The difference in energy. You ready? This goes by pretty quickly, so watch carefully. I'm going to bang on the atom, and you'll see it get excited and then de-excite. Here we go. As the electron drops to lower energy levels, it spits off a photon to conserve energy. Here's another one. Just one photon that time. Here's another one. Exciting? De-excite. Every time the electron drops down an energy level, like going downstairs, it emits a photon. And notice that it can only emit photons of certain energies equal to the energy differences between one level and another. There's a certain specific energy difference between the levels, and that determines what the energy of the photon must be. Now I think it's time to go do my demo. And so I am going to ask you to get those little slides out. I brought some lamps with atoms inside the lamp, and I'm going to put it here. I hope it doesn't break. I don't know if it will or won't. And if we could have the room lights dimmed a little bit, maybe a lot even in the back. Yeah, that's kind of good. I'm going to try to turn on different, oh, cool. I'm going to try to turn on different lamps. And you should look at them through your diffraction grating. It's like a prism. And if you orient it the right way, you should see a set of emission lines. Do you see them? This lamp, I think, is hydrogen, but I can't tell for sure. Do you see 4 lines like hydrogen should have? Yeah. Can you orient your diffraction grating to see the spectral lines from hydrogen? Ready for helium? Here we go. Can you see it? Do you see the spectral lines? Here, let me try your. I'm going to try it myself. Oh, yeah. Yeah, what you have to do if you're not successful, you look through this, but you have to look either off to the right or off to the left. And you have to orient it so that you see vertical lines to the left or to the right. Like that. You want to turn off the lights? Okay, could you turn off all those lights? Does that help? Can you see the spectral lines from helium? All right, here's, I think, mercury. How does that look? Less lines? Oh, yeah. Cool. Here's another one. Every atom has its own set of energy levels, and when the electrons drop down from a higher energy level to a lower energy level, you get to see the energy difference between those two energy levels, because the electron drops down and spits off a photon having an energy equal to the difference in energy between the two energy levels. I might have one more here. You ready? I forget what this one is. Can you see lines in that one? This one is, if I had a flashlight, I could see. Let me see if I can. No, I don't know what this one is. You have a flashlight? Ooh, good. I can't tell you what atom it is because oh, thank you. Oh, this is nitrogen. So this one is neon. And this is molecular hydrogen. And this one is helium. That's the best one, I think. And then here's simple hydrogen. You should be able to see, like we showed before, 4 or 5 maybe emission lines. Can I take a look in yours? Can you see 4 or 5 emission lines? Oh, I see way more than that. Yeah. Cool. Let me see if I've got this right. Oh, I'm wrong. I apologize. This one you're looking at right here is the atom mercury. So this is actually mercury. That's why it has so many emission lines. This looks a little bit like the fluorescent light bulbs that you see out, you know, in the seedy districts of some downtown area. But that's mercury. You can see how many energy levels there must be in a mercury atom because each one of those energy levels allows the electron to drop down different distances, different amounts of energy, so that it can emit lots of different wavelengths of photons. By the way, I don't know if you guys on the side can see. There, you get a quick look. Is that better for you over there? Can you see the mercury lines now? And now these folks over here. Whoa, we almost lost the mercury. Does that help you guys over there? Can you see them? All right, if we could have the room lights up. That's the end of today's lecture. And next time we'll talk about thermal emission from solids and infrared light. Please pass your diffraction